But we're going to now see how we can relate volume of gases to moles and mass and particles as well. So we can, if I give you the volume of a gas at STP, and that is the key, folks, right here. It has to be at STP. If we're not at STP, we do something else, and we'll see how that is here today. Okay? So keep that in mind as we go through this. We can now relate mass to volume of a gas. We can relate mass of one, like a solid, to then figure out how to get to the gas of it using the ideal gas law. All right, so you can start from a solid, and you can get to a gas as well and do all this different stoichiometry. That's why stoichiometry is so important. All right, but let's talk about it, guys. Molar volume. Get your reference packets out. You're going to need them today. I want you to see that you don't have to memorize this number, but 1 mole of any gas. It does not mean it's just one gas or it has to be Brinklov. It's any gas. The only caveat, folks, is it has to be at standard temperature and pressure. In this classroom right now, here in Greensboro, are we at STP? What's standard temperature? 0 degrees Celsius. I know it's cold in here. You guys tell me every day. Are we at 0 degrees Celsius, though? No, we're not at 32 degrees Fahrenheit in here. You may think we are, but we're about, balmy 60 degrees. All right? It's warm in here. Warm enough. Are we at standard pressure? Meaning, are we at sea level? No, we don't have the ocean out next to us yet. Global warming, you never know. Someday. We'll see. All right. So, anyway, folks, you get the idea. We're not always at STP, so there's not going to be a ton of times where we can actually use this. All right, but if we are at STP, we can. All right, you got to read your conditions in your problem to see if you actually are at STP or not. But then it's pretty simple. 1 mole of any gas equals 22.4 liters. All right, so if you're at STP, the work gets a little bit easier. If you're not, it gets a little bit more challenging. You got to use the ideal gas law. Let's try an example. It says, what is the mass of 98 milliliters of sulfur dioxide at STP? What do we have to start with?
98 milliliters.
All right, we'll jot that down. There's our given, 98.0 milliliters of SO2. What do you notice right there? So first off, what are our conditions? STP. So can we use that? Absolutely. 1 mole equals 22.4 liters when you're at STP and we're at STP. What's the big glaring difference between what we have and what we can use? Yeah, one's in milliliters and one is in liters. So what's our first step we have to do? Switch it to liters. So guys, we can just do it all in one long conversion. All right, that's why we've learned this dimensional analysis. Milliliters will go on the bottom, liters will go on the top. Which one is the base unit? This is back to review from Unit 1. Which one is the base unit? Liters, right? Because base unit means the one that has no prefix. The base unit, folks, we said always gets the number 1. Then our prefix is the one that gets the power 1. Well, what's the power for milliliters? 10 to the negative 3. All right, 10 to the negative 3. So, we have now successfully converted between milliliters and liters. So now, folks, we can just start to do our whole roadmap. If we take a look back, we're starting right here. Give me a second here. We're starting up on this end with volume of a gas. So, can we go right from volume to mass directly? Does that road go that way? No, it doesn't. It has to go down here, then over, right? Here to here. So it's going to be a two-step problem. That doesn't work. So what do we have to go back to first? Moles, guys. And again, that's review for us from Unit 8. You always have to go back to moles first. So we have liters. Well, how do we get from liters to moles? Well, liters has to go where? On the bottom. Moles will go on the top. Using our conversion factor that we have right here, we said that 1 mole is how many liters? 22.4. Liters are canceled out. We're left with moles. Is moles what we're trying to get to in this problem? Is it? What are we trying to get to? Mass, which what's the unit of mass, folks? We're trying to get to grams. All right? So we've got to do one more step. Moles will be on the bottom. Do moles and grams relate? Absolutely. We've done that extensively. You just did that in your bell work. Which one? When you have moles and grams in the same fraction, which one gets the number 1? 1 mole. So for sulfur dioxide, what's our formula for sulfur dioxide? SO2. We've got to figure out the molar mass. Lauren says 64 point what? 07. Now all you have to do, guys, is do the math. Top times top, divide by bottom, we get you the right answer. So when we make that change from 10 to the minus 3, because you guys led me astray, it wasn't my fault, it was you. All right. What do we get for a final answer? Don't mumble. Speak loud. Ellie. 0.28, you say?
You did
0.028? No, that doesn't sound right. Should be 0.28. 0.28 was the answer there. You guys are trying the next one. All right, so we're starting with milliliters again. We've got to go back to liters first. All right, so that means mils on the bottom, liters on the top. 1 liter has got 10 to the third milliliters. All right. Then we are at STP, so that makes our work a little bit easier. Liters on the bottom, 1 mole on the top, 22.4 liters. Then we're trying to figure out mass again, which is grams. So 1 mole of oxygen's on the bottom, grams of oxygen on the top. That's going to be O2, which is 32.00. When you go ahead and do the math, what do we get for an answer? 19 grams of O2. You've got to have all that for your proper units. Folks, is this a lot of new stuff here? It's stoichiometry that we've done. The only new piece is this conversion factor right here. That's the only new piece there for us. All right. That's it. Moving on. Let's try another one. Question. So we're starting with mass here. We've got fluorine. What's the formula for fluorine?
F2.
F2. All right, so that's going to be 38.0 grams of fluorine on the bottom. Takes you back to moles of F2. All right, it does say liters. All right, so we don't need to worry about that. 1 mole of F2 is going to be 22.4 liters of F2 because, again, we are at STP. So no matter what gas you have, it is 22.4 liters. When you go ahead and do the math, what do you get for a final answer?
44.8 liters.
These will actually reduce down to 2 and 1. 44.8 liters of fluorine. Easy? All right, now do you think we're always going to be at STP, folks? No, so this is, you can only use this when you're at STP. When you're not at STP, what do you have to use to figure out grams or liters that you've already learned about?
Oh, it's
Not the ratio that you learned about on Monday. Not Dalton's. What'd you say, Ellie? The ideal gas law, guys. So when you're not at STP, you use the ideal gas law. Shh. Why is there so much talking? Now, the last couple new things, folks, is calculating the density of a gas. All right, when we're at STP, again, it's super easy. You're going to find that STP makes things so much easier. If we could be at STP all the time, that'd be awesome. But if not, well, then we've got some more work to do. So we'll do the STP first. What is our density formula, guys, just in general? D equals M over V. So when we're at STP, we can take the molar mass, which we've already learned about, and we can take the molar volume, which we've just learned about, and that's it. It's that simple when you're at STP. But when we're not at STP, that's where we can't just say, oh, the volume is 22.4 liters per mole, but we have to do some more work. All right? Here we go. Calculate the density of carbon dioxide when you're at STP. It's pretty easy. D equals M over V. Molar mass over molar volume. So what's our molar mass of carbon dioxide? 44.01 grams per mole. What's our molar volume at STP? 22.4 liters per mole. Moles are going to be canceled out, guys, so we're left with grams per liter, which is a good density unit. 44.01 divided by 22.4. What do we get for a final answer?
1 point, or I would just say 2.
1.96.
Sig figs, we'd have to go to 3, 1.96.
Yeah, not
All right, 1.96. You guys try the next one. So this problem, we're looking for the molar mass. All right, now it doesn't say at STP. I'm telling you this is at STP. All right, it's a typo. So D equals mass over volume. We're looking for the mass now. So mass is going to be D times V. So molar mass equals our density, which is 1.56 grams per liter, multiplied by 22.4 liters over moles. Liters will cancel out. We're left with grams per mole, which is a good molar mass unit. You take 1.56 and you multiply it by 22.4. What do we get for our final answer? 34.1 grams per mole. I'm sorry, 9. My apologies. Holy cow, folks.
You get that answer not correct.
Yeah, you did just say that.
All right, we're not always at STP, so most of the time, this is what we're going to have to do. All right, our density, this is derived from the ideal gas law. Density equals P. What's P? Pressure. M. What's M? Molar mass. What's R? That's our gas constant. And T is temperature, okay? Now, what do we have to know about temperature? Has to be in Kelvin. Why? Because of our gas constant. All right, pressure needs to be
Kelvin.
Pressure needs to be Kelvin.
Temperature. Oh.
Now, atmospheres, guys, or if you decide to use a different constant, you can keep the pressure that matches it. That's fine. That's on you. I will always use atmospheres. All right, so it says, what is the density? That's what I'm looking for. Get back to writing your variables out. Of ammonia at pressure of 800 torr. Right away, I'm going to convert this to atmospheres, so divide by 760. All right. 800 torr, guys, divide that by 760 to get it back to atmospheres. What do you get? All right, 1.05 ATM, because we're going to use R equals 0.0821 latum over mole. Okay? Now, M is my molar mass. Well, what's my molar mass for ammonia? 17.034. All right. No, 24. Should be 24. All right. No, you're right. It is 3.4. I'm just like all over the place here today. What's our unit there for molar mass, guys? Grams per mole. And then the last one here is temperature, which we are given. It's 25 degrees Celsius. What do we have to do to that? 298 Kelvin. Okay? So, folks, we have all four. All we have to do is plug it into that formula. There's no rearranging that we have to do because we're looking for density. So 1.05 ATM times our molar mass, which is 17.034 grams per mole, all over our R value of 0.0821 liters times atmospheres over moles times Kelvin. All right? Moles are going to cancel out. Atmospheres are going to cancel out. And then we have our temperature, which is 298 Kelvin. That's going to cancel out because it's on the bottom of this one. It's on the top there. So we're only left, guys, with our units of grams on the top here, liters on the bottom. Well, that hopefully should be good for us because it's grams per liter is our density unit. Go ahead and do the math. It's just plug and chug at this point, folks. What do we get? 0.73. That's it, guys. Now, it's not the same density that we're used to, but is it really a whole lot different than what we've been doing this whole unit? You're given four knowns, and you're solving for one known, guys. The only caveat here with density is this formula right here and Graham's law. Those are the two that are not in your reference packet. You've got to memorize. All right, you've got to memorize these for your quiz tomorrow and your test. All right? So, here we go. Let's do some more practice. Stoichiometry says how many liters of oxygen are required to react with 0.35 liters of propane at STP. All right, so two ideas to think about. We could use molar volume, or we'd have to use the ideal gas law. Which are we going to have to use here? First off, when will we use molar volume at STP? When will we have to use ideal gas law? When you're not at STP. So, in this problem, which one are we going to use? Molar volume, which is just going to be, basic stoichiometry, or are we going to use the ideal gas law? Which is it?
Ideal gas.
Why do you say ideal gas? Are we? Folks, read the problem. What is it? What are we at? We're at STP. Yours does. Since we're at STP, we only have to use molar volume. All right? Go ahead and work this problem out. So, what's different about this one, guys? This is like a gram-to-gram problem that we've done in the past, except it's liter to liter. So it's still going to be all the steps through, except instead of going from gram to gram, we're going from liters to liters. What do we have to go to first, regardless? We have to get back to moles, right? So that's going to be liters of C3H8, right? Propane. How many were like, what is propane? But guys, if you take a look at everything else in there, you know the names of those. You know it's oxygen, you know it's carbon dioxide, you know it's water. So by process of elimination, you can determine that C3H8 has to be propane. All right? So moles of C3H8 will be on the top. 1 mole is how many liters at STP? 22.4, okay? So, we've done this. We're trying to go from one substance, trying to go from propane to oxygen, guys. So when we're going from one substance to another, what do we use? Mole ratio, guys. That's what we've done already with stoichiometry. This is a review. It's a new context, but the problem in the process is the same. So we need moles of C3H8, then moles of O2 on the top. Is everybody with me? Right? Now, mole ratio. Where do we get the mole ratio from? The coefficients. So we've got moles of oxygen. What's my coefficient there? 5. What's my coefficient for propane? 1. Right? Coefficients are out in front. All right, so now I've gone from propane to moles of oxygen. But do I want to stay with moles of oxygen? No, I want to go to liters of oxygen. So I'm going to have 1 mole of oxygen on the bottom, liters of oxygen on the top. Well, in 1 mole of oxygen at STP, how many liters do I have? 22.4. Notice, this math isn't going to be that bad because 22.4 is going to cancel out. So it's really just 5 times 0.35. So our final answer is going to be what? 1.75 liters of oxygen. Again, this is why stoichiometry is so important, because we can say, if I have X number of liters of one substance, how much will I need to completely react that to produce my reaction that I want to get to? A little bit new context dealing with liters instead of grams, guys, but the process is the same. If you mastered stoichiometry back in Unit 8, this is super easy for you. Should be. If you're struggling, what do you need to do? Come in and get some help, guys. I'm here tomorrow morning. Nobody was here today. I'm here again tomorrow morning. If you got questions, come in and see me. All right, let's take a look at another example. All right, is this one in your notes? I know. All right, guys, it says how many grams this time. So grams is G. Calcium carbonate. So this is where knowing your naming rules comes into play, folks. You've got to know how to name. What is calcium carbonate? Yeah, so there's your calcium carbonate right there. Must decompose. So what type of reaction do we have? Which is called a what? What type of reaction? Decomposition. See all this review that's coming back into play here. Right, so it would be decomposition. It makes it easy. 5 liters of carbon dioxide at STP. So what can we use here when it says at STP? molar volume. We don't have to use the ideal gas law. So, go ahead, folks. You're going from liters to grams. All right? Try this on your own first. All right, so we're starting with 5 liters of CO2. So again, you've got to get in the habit, guys, of keeping your substance there as well because you're dealing with multiple different compounds. So we're at STP, so we can use 22.4 liters. Get back to moles first. That's always your first step when it comes to stoichiometry. Get to moles, because without that, you can't compare anything. So, 22.4 liters of CO2 is 1 mole of carbon dioxide. All right, now we can look at our mole ratio. Moles of CO2 to moles of calcium carbonate. All right, where do we get the numbers for those moles there? All right, coefficients. Is this a balanced equation, or did you just assume it was balanced?
I assume.
Who assumed it was balanced? It's okay.
Definitely is.
This case, guys, it worked out. This is balanced, but throwing it out there, it's probably not always going to be balanced. All right. So 1 and 1. Now we can go then to grams. So 1 mole of calcium carbonate is a certain number of grams of calcium carbonate, and it's about what? It's about 100. It's like 100.08.
09.
All right. So when you go ahead and do this, 5 times 100.09 divided by 22.4 liters, what do we get for a final answer? Grams of calcium carbonate? 22 with sig figs? 22 grams of calcium carbonate. So if we wanted to produce 5 liters of carbon dioxide, we would need 22 grams of calcium carbonate to do that. All right? Questions? It's all coming back now, guys. Stoichiometry, told you, we're going to be using it the rest of the year. Let's take a look at another example. You guys try this one first. You have to write the balanced equation here. Balanced equation, we take 10.0 grams of LiCl. We're trying to figure out how many liters of Cl2 gas we are at STP. That makes our work a little bit easier. So we've got grams of LiCl, moles of LiCl at the top. What's our molar mass for lithium chloride? What's that?
70.9.
Nope.
42.391.
42.39. All right, now to be our mole ratio. So moles of LiCl to moles of Cl2. All right, if we look at it, chlorine is 1, lithium chloride is a 2. We can reduce that down if you want to. You don't have to, but that'll be 5 over here, and the 2 is now a 1. All right, then we're going to continue along. We're trying to get, we have moles of Cl2, but are we trying to go to grams or are we trying to go to liters? So it's going to be 22.4 liters of chlorine on the top. Since we're at STP, we'll go ahead and do that. Our final answer you should get is 2 point what? That doesn't seem right. 6.4 liters of chlorine. Questions?